All right, everybody. Let's talk first about the take-home exam. Everyone got a copy of that? Anybody have any questions? No? Have you all had an opportunity to kind of breeze through all the questions? Do they all seem like they're within concepts that you are familiar with?
Oh yeah, definitely. Some of them are going to be a little rough, but they all look doable.
Okay. Yeah, I was thinking about it. You know, it's going to be due on Easter Sunday. I kind of forgot that it's Easter Sunday. So, you know, maybe get it done before Sunday if you've got plans. I apologize, but I'm not trying to ruin your Easter, but I'm also trying to make sure I can get grades back to people in time, you know, for the drop date, just in case you're considering that. So, okay, we're going to get right down to business. We're going to continue 8.2. We had talked about the geometric series, and I had taken some time to show you kind of where the idea of finding the sum of the series comes from. And we have this general formula that if we have that series that looks, it has to look like this in order for us to call it a geometric series. But if we do have it, then we can identify A and R. And as soon as we know that the absolute value of R is less than 1, we know we have convergence and that it will actually converge to a number. And we can calculate that number, A over 1 minus R. And if the absolute value of R is bigger than or equal to 1, it's going to diverge. All right. So when it comes to series, all right, there are only 2 types of series that we can find the sums of in this class. All right. There's only 2. Geometric, and then what's coming in a minute. All right. So that's actually important information for you, because if I ask you on a test, the final, to find the sum of a series, you're going to know it has to be one of those 2 types of series. It's either one or the other. If I ask you if a series converges or diverges, then that means you probably can't find the sum, which means it's probably not one of those 2. All right. That's kind of like a subtle little hint in a problem. If I ask you to find the sum, it's either geometric or, as you'll see, what we call telescopic. Okay, so here we go. I want to do just maybe one more example of this. Let's just pick this one here. Oh, I got to reopen my program. Give me a second. There it is. All right, why don't we do this one here? This one looks fun. I was not very prepared for today. I was sitting here about to get a couple things ready, and then a bird hit my window in the back. Heard something really loud, couldn't figure out what it was. It's a bird. Okay, so here we go. So I ask you on this problem to determine whether or not this, you know, is a geometric series and whether or not it converges or diverges. So we know that we need to try and get this to look like sum n equals 1 to infinity a times r to the n minus 1. All right, that's what all geometric series look like. So right now, the thing that's making me think that this is geometric, other than the fact that I said, you know, find this if this geometric series converges or diverges, is the fact that I'm seeing n's up in the exponent. That's kind of like what the format of a geometric series looks like. The n, the thing that keeps changing, is in the exponent of the expression. So I'm going to try and make this look like this. So here's what I'll do. How about we rewrite this top one, -4 to the n minus 2. Why don't we write it as n minus 1 plus 1 minus 2? In other words, I'm putting in this -1 plus 1 so that I can make it look like an n minus 1. And then on the bottom, I'm going to do the same thing. I'm going to rewrite that 7 as a 7 to the n minus 1 plus 1 plus 1. So I introduce this -1 plus 1 again so that I can make it look like an n minus 1. So we've been doing that, we've done it a few times in the past. Now we're doing it, more frequently with these geometric series. Get used to it because it's very common. And now what I'll do is I'll split it. So I'm going to split it here and here. So I should get a -4 to the n minus 1, and then a -4 to the what? I still have
-1.
Right? Yeah, 1 minus 2 is -1. So we'll put -1 there. And then on the bottom, we'll have a 7 to the n minus 1 times 7 to the, let's see, 1 plus 1, right? So 2, 7 squared. Notice that the 4 to the -1, sorry, -4 to the -1 and 7 to the second power, those are just numbers, right? Those are just numbers. So, and then these two are actually both raised to the n minus 1 now, so I should be able to put those two together. So it should look like this now. Sum n equals 1 to infinity. Let me work with the numbers first. This -4 to the -1 is really the same as 1 over -4, right? And so I'm going to put that on the bottom. I'm going to move the -4 to the bottom with a 7 squared. 7 squared is 49. So let's, well, let me write it down. I'll have 1 over -4 times 1 over 49. And then I have the -4 over 7. Both of them are raised to the n minus 1. So I put them together in a fraction. As a fraction, I put both of those together like this. And then this became those two. So now I have sum n equals 1 to infinity. Let's see, this becomes -1 over 4 times 49. What's that? 196, I think.
Yeah, 196.
196. And then I have -4 over 7 to the n minus 1. And now it looks geometric, right? This looks geometric. Do you all see that? Do you understand now that I've got it to this, what I was trying to do from the beginning, trying to get it, everything to the n minus 1s, everything that's not, affected by the n out front as a number. This is my A. This is my R. So a quick check. I take the absolute value of R. I need to make sure, see if it's less than 1, which it is, right? The absolute value of -4 over 7 is 4 over 7, and that is definitely less than 1. So we are going to get convergence, right? This will be a convergent geometric series. So this converges. And what does it converge to? A over 1 minus R. So for us, that's -1 over 196 over 1 minus R, but R is, careful, R is -4/7, right? R is not positive. The absolute value of R is positive, but the R itself is -4 over 7. So that's going to give me -1 over 196 over 1 plus 4/7. So -1 over 196 over, get a common denominator here. So what's that? 11 over 7, something like that. And then just multiply by the reciprocal, 7 over 11, like that. And this should give you -7 over, what is that? I'm just gonna use my calculator. I don't feel like trying that in my head right now. 6 times 11, yeah. 2156. There you go. You're converging to a negative number. The sum of this series converges to a negative number. I wonder why. It's because I have a negative number in here being raised to a power, right? Negative to a power. And so as I start changing the values of n, it's going to alternate. It's going to be an alternating series. You're going to have positives and negatives. It's going to be like plus minus, plus minus, plus minus, because every time I raise this to an even number, I'll have positive up top. Anytime I raise to an odd, it'll be negative. So I'm adding, subtracting, adding, subtracting, adding, subtracting. And when I do that, it winds up totaling out. The infinite sum turns out to be more negative than it is positive. And it converges to -7/2156. Any questions on that? Okay.
Oh, I didn't have a question, sir.
Yes.
I wasn't here last class period. I did went over the lecture. So
Yeah.
we're just trying to get it to look like that. What is it? Up there, right? That's all we're trying to do. And what we did is use the power rules just to
Exponent properties.
yeah, there you go. Exponent properties to make it look like that, right?
Yep, exactly.
Okay, sounds good.
And you know, when I did this, when I had n-2 and I wrote it as n-1 plus 1 to realize this hidden 0 here, you could have just said this is n-1 minus 1. Like if you just think about what n-2 is, it's n-1 minus 1.
Right.
That's the same thing. I personally always just subtract 1, add 1. That's just, I always do that. Because when you have n plus 1, I guess you would have to realize that's n-1 plus 2, right? So if you're not doing that mentally, you just write it down, you get the same result.
Okay.
Yeah.
And when it converges, it's like when the absolute value of r is less than 1, we do the a over 1 minus r every time.
Yep. You only do this if you have that absolute value of r less than 1.
And then if it's greater, it just diverges. Yep.
So what if this would have been, let's say, -7/4, the other way around? Then 7/4 would be bigger than 1, and then all you'd say is it diverges and you're done.
All right.
Yep. Okay, so that's geometric series. I want to kind of throw a little twist into this, okay? When we look at this sum, a little twist here, all right? Don't freak out about this. This is the generic formula we have for geometric series, right? And if I were to start plugging in, you know, n equals 1, n equals 2, n equals 3, this is what the geometric series looks like. All right? So that's what we learned last class. I want to show you that there's another way to create this same series with a slightly different looking sigma notation. So just tell me if you believe this or not. If I write this instead, sum n equals 0 to infinity, a r to the n, that it will create the exact same thing. Now, we've never started at 1, we've never started at any number other than 1 before. When we first started talking about sequences in 8.1, we said, we'll always start with n being 1. But I think I told you in class, there will be a point where we actually relax that restriction and we can start n wherever we want it to start. If I choose to start it at 0, if I choose to do that, and I change the formula from AR to the n minus 1 to AR to the n, notice it creates the same thing. So if I plug in 0, R to the 0 is 1, and then we get A times 1 is A. And now I let n be 1. So AR to the 1, that's just AR. And then AR to the 2, right? So AR squared plus ... and that's exactly the same, right? They're equal. What I'm trying to get you to see is that there's multiple ways to represent a geometric series, this way or this way. Those are two ways you can do it because they create the exact same series. So in your,
what about +1?
You could do a +1. What do you mean? Yeah, you could do a +1, but you would have to start with a negative n.
So theoretically, you could shift its starting point as far as you want,
Yes.
and it would just shuffle that. Okay, interesting.
Now these two are the ones we use most frequently. Okay, these are the two that we use the most. Either start at 0 or start at 1. All right. So I guess what I'm trying to get at is if we did this same problem, let's say we did this exact same problem. Let me copy it. What if it was this exact same problem? All right. But when it was presented to you, they started at 0, not 1. Then what you would be wanting to do then is make it look like this, okay? Where you have a power of n on top instead of n-1. That actually might be easier because then you would do this. You would just do -4 to the n times -4 squared over 7 to the n times 7 to the 1. Do you see how I no longer need to do the -1 + 1? Because in the formula, I need it to be an n, not n-1. You all see that?
Shouldn't it be divided by -4 squared? Since you're
Sorry,
subtracting
I
the
forgot to put the
exponent?
negative. I'm sorry, I forgot to put the negative
or
on
that.
there. Sorry, yeah, I just forgot the negative on there. Now this is going to give you a different answer. Like this is going to converge to something different because this is slightly different than what we had before. Look, but the problem is different. Okay, I gave you I started the series out at a different place. So you should get a slightly different answer. What I'm trying to get you to see is that if you start at 0, then what you're trying to achieve is different. You're not trying to get n-1, you're trying to get n here.
Professor, I have a question.
Yes.
If let's say at the end you get that result, and then you want to go ahead and convert it back to n = 1, is there any way you can do that at the final result?
Yes. Is there a way that you can convert the series back? Okay, so yeah, let me show you. I mean, we're going to do this later, but I'll show it to you right now. Okay, we may as well. So you see this geometric series right here, right? You see this geometric series? This is what I just gave you, right? What if we had no idea of the existence of the original one? Okay, that's this one. What if we had no idea that this one existed? And all we knew is this one, right? Let's just act like that's all we know. And then I said, hey, look, I'd like for you to rewrite this series up here, but I would like for it to start at 1 instead of starting at 0. How do I do that, right? I think that's your question, Lewis. Is there a way that I can switch it? So here's how we do it. So the question is, what would that formula look like? So and this is weird, okay? Just check this out. What I'm gonna do is this. Everywhere I see an n in this formula, everywhere I see an n, I'm gonna replace it with n-1. Why? Why? Because look at that equation right there. If I replace the n with n-1, it now becomes n-1 = 0, doesn't it? And if I add 1 to both sides, I will get n = 1, which is this, right? So rewrite this formula, here, I'll just do it slowly. If I rewrite that formula and I replace all the n's with n-1s, that's what it would look like. And then on that bottom of that sigma, if I add 1 to both sides, I get n = 1 to infinity ar to the n-1, which is the formula we were acting like we didn't know existed. So what I'm getting at is if your index on a series, if your index starts at 0 and you would like for it to start at 1, you will just replace n with n-1. If your series starts at 0, but you would like to start it at 2, you would replace n with n minus 2. If your series starts at 1 and you want to have it start at 0, you'd replace n with what? What if your series starts at 1, but you want it to start at 0? What would you replace n with? If my series starts at 1, but
Would
I'd
you
like
replace
for
it with
to
n plus 1?
I would like for it to start at 0, right? What do? I replace n with n plus 1. Why? Because if I replace that with n plus 1 equals 1, I subtract 1 from both sides and I get n equals 0. It's a little weird. We'll do it more later, so it'll come back. But yes, there is a way to take a series and switch it to start at a different place. Okay, let's continue. All right, so up to this point, we should have some idea of what a geometric series is, how to go about finding whether or not it converges or diverges. A problem like this, the first thing you have to do is you have to figure out the formula that creates the series. Once you find the formula, then you can go and tweak it and make it turn into the a r to the n minus 1 thing. But you have to first come up with a formula that creates that, which is tied into what we were doing in 8.1 in finding formulas for sequences. And that's on your test. I gave you kind of an easy one and a hard one on the test for finding the formula. And then this one right here, we did in class. We did one like that in class last time. Okay, we are moving on. Let's talk about the next series. Right now, we understand the basic idea of a series, right? What a series is, an infinite series. We know of one particular type called geometric that we can actually find the sum of. And now we talk about a new type of series called harmonic. And I've got great news. Harmonic is simple, easy, all right? A harmonic series is any series of the form sum n equals 1 to infinity, where you have a constant on top, a number, and some linear expression in n on the bottom. All of these are examples. Notice on the first example, sum n equals 1 to infinity, 1 over n. 1 on top is a constant, n on the bottom, well, that's just n, right? It's not n squared, it's not the square root of n. N by itself is linear, it's n to the first power, right? That's a harmonic series. Here, 4 over 2n plus 1, constant on top, linear on the bottom. Next one, -5, that's a constant, over n plus 5, that's linear. Good news. All harmonic series diverge. They all diverge, okay? I'm going to prove it for only one of these, okay? I'm only going to prove it for one of these, and then you're just going to have to believe that there's a way to prove it for all of them, all right? So would y'all like me to prove to you why this diverges all the time? Would y'all like to see that? Okay. All right, so I want to show you right now, I want to show, WTS, want to show that this series, sum n equals 1 to infinity of 1 over n diverges. Now, the way I'm going to show this is a little weird, okay? Because it's a proof, but it's a proof. It's a proof. It's not a proof. It's just an odd proof, I guess. Sorry, my phone has been going all day today. It's weird. All right, so let's write out the terms of this. Now, this is going to get really, really ugly. I would like to write out, the terms of this series. So let's start writing it out. 1 over n. All right, so plug in 1, you get 1. Plus, plug in 2, you get a half. I'm going to do a bunch of these. A third, a fourth, a fifth. Man, why is it doing that? a sixth, a seventh. I'm going to go all the way out to 16. An eighth, a ninth, a 10th, an 11th, a 12th, a 13th, a 14th, a 15th, a 16th, plus dot, dot, dot. All right. I'm trying to figure out what this is. All right. Like what this adds up to be. All right. Trying to figure out what this adds up to be. So let's see here. I want you to look at just those two fractions right there. Just those two. All right. Do you agree or disagree with me on this? Those two, okay, are larger than, this is larger, this is larger than 1/4 plus 1/4. So 1/3 plus 1/4 is bigger than 1/4 plus 1/4. Yeah, do you agree? Yeah, yes, yes. Okay, but what's 1/4 plus 1/4? A half, right? So those two together, 1/3 plus 1/4 is bigger than 1/4 plus 1/4, but that's equal to a half. I'd like for you to do the same thing for the next, not two, but for the next 4. Do you agree that this is larger than 1/8 plus 1/8 plus 1/8 plus 1/8? See, when you look at these numbers, 1/5, 1/6, 1/7, 1/8, 1/8 is the smallest one in that list, right? 1/8 is the smallest one. And so if I add these up, it should be bigger than, right? Larger than adding up 4 1/8s together. But what are 4 1/8s added up? Well, that's 4/8, right? And 4/8 is a half. Understand so far? So I took these two, right? I took those two and I did that. And then I took these 4 and I did it again. How many do you think I'm about to take now?
8.
The next 8. I'm going to take the next 8 of them and do them. So the next 8 of them are all of these. Okay, if I take all 8 of these, that added together is larger than what?
1/16.
1/16 added 8 times. See, I'm going to look at the smallest number here. So this is larger than, not that, larger than 1/16 plus 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 1/16. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's 8/16, right? Add all those up, that's 8 of them. So those together is also a half. And now I'm going to do it again, but I'm going to take the next how many?
16.
16. And then after I do that again, I'm going to take the next 32. And then I'm going to take the next 64. And then the next 128. Understand? I could continue to do this forever, couldn't I? You'll agree I could continue to do this? So what you're saying to me then is that what's in yellow is bigger than a half. What's in blue is bigger than a half. What's in green is bigger than a half, right? And I could keep doing that forever. So essentially what you're saying to me is that this sum that I'm looking for, 1/n, must be bigger than, well, let's start. 1 plus the next one was a half, right? So that's the first 2 right there. Okay. This sum that we're looking for is bigger than 1 plus a half plus what? A bunch of, just a half, keep going, right? Half, 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 forever. And what's a half plus a half plus a half forever headed towards?
Infinity, isn't it?
Infinity, right? Because when you think about these, are these headed to 0? Are those guys headed to 0?
No.
No. In the nth term test, the nth term test says that in order to have any sort of convergence, you've got to have these things headed to 0. If it heads to somewhere other than 0, it diverges. So this is all becoming infinitely large, isn't it? And the sum that we're looking for must be bigger than that. And the only way to be bigger than infinity is if you're infinity yourself, right?
It's especially weird seeing as the limit of this takes us to 0.
Yes. The limit of this, when you say that, the limit of the sequence.
Yeah, the
We
limit
know
of the
that-
sequence.
We know
Yes.
that goes to 0, but we learned last time that just because the sequence goes to 0,
Yes.
that doesn't tell you anything about the convergence or divergence of the series.
Yes. It's just really interesting.
Yeah. Okay. That's it. We're done. Harmonic series diverge. We move on. This is a
So what do
visual.
we have to do to prove that test?
You just have to say it's harmonic. Done. So you have to identify that it's a constant over a linear expression in n. That's what you, as soon as you see it's constant over a linear expression in n, you can say this harmonic series, therefore it diverges, and you're done. All right, this is just a little visual just to convince you that I'm not lying. So here on the left is the sequence 1 over n. So there 1 over n heads to 0. But if we start adding them up, here's what happens. And you can see as I move to the right, see the number on the right, this is our sum. Our sum is getting bigger and bigger and bigger the further out we go. It's not asymptotic. It just keeps growing without bound. It becomes infinite. Now we got to go really far out to make it grow. But I mean, we have an infinite number of terms, so we can do that. All right. Geometric, check. Harmonic, check. Telescopic and collapsing. All right, so I'm not even going to open up the note on that until I remind you of something. Last class, what we said is that when you have a series, right, that the series looks like this. You're adding up all these guys forever, right? That's an infinite series. We're interested in knowing what this does, right? Does it converge or not? That's a general idea from last class, at the very beginning. That's what a series is. Now, I said that we could create this new sequence. We called it S sub 1. That's just the first guy. S sub 2 was the first 2 added up. S sub 3 was the first 3 added up. And we could continue this till we get to S sub n, which would be the first n of these added up. We called it the nth partial sum. And we said this: if the limit as n goes to infinity of this S sub n, whatever this is, if that goes to some number s, okay, if it converges to some number s, then this s is this sum, okay? The problem we ran into was that I told you it's very hard, generally speaking, to come up with a formula for S sub n. With the geometric series, I was able to do it. I was able to come up with a formula. It was very tricky the way I did it, but I was able to come up with a formula for S sub n. So I was then able to take the limit and I was able to figure out what it converged to, a over 1 minus r. So long as the absolute value of r was less than 1, that's what a geometric series does. But generally speaking, for us to figure out what a series converges to, we must be able to come up with this formula and then take its limit, right? Is that okay? Let's now take a look at the next series. Telescopic or collapsing series. So these are special series where when they converge, we can find the sum. When they converge, we can actually find the sum. So I told you in the beginning of class today, there are only two types of series we can find the sums of. Geometric. When a geometric series converges, we can find its sum, a over 1 minus r. The only other series we can ever find the sum of is a convergent, a convergent telescopic series. Or we call it telescopic or collapsing. You'll see why we call it that in a minute. But that's it. Those are the only two in this class that we can actually find the sum of. So the best way to explain to you what a telescopic or collapsing series is, or how to go about them, is to actually do one, all right? Because you just have to see it, all right? You just have to see it. So here we go. These are fun. Fun is relative, isn't it? All right, so Here we go. The instructions here are just to figure out what this does, okay? So does this converge? If it does, can you tell me what it adds up to be? So let's first start kind of thinking about things. This is not geometric. How do I know it's not geometric? Well, I don't see ends up in exponents, right? The ends are not in an exponent. So I know it's not geometric. It's not harmonic as well, because I don't have a constant over linear, right? I actually have a constant over quadratic, right? So I know it's not geometric. I know it's not harmonic. The next thing I think about is, well, let me just real quick run the nth term test. Let me just run the nth term. When I run the nth term, what I do is I take the limit as n goes to infinity of the sequence 1 over n squared plus n, but that goes to 0, obviously, because we have fixed over infinity. And that tells us
it's indeterminate.
It tells us nothing, right?
Yeah.
This basically fails, okay? This fails to give us any information, right? Because it goes to 0. Now, had that gone to 1, we'd be done, right? We'd say, oh, it diverges. But this test fails. Okay, but I wanted to think about it because I didn't want to skip that step and do all this work on something that I could have solved in the very beginning. So unfortunately, that doesn't help. So we look at it and we go, what the hell, man? What the hell? Okay, so now I have to show you this. Sometimes, like in math, you just got to see things first time, right? And then you're like, okay, now I know I can do that. I'm going to take the 1 over n squared plus n, and I'm going to do partial fraction decomposition on it, just like we did back when we were doing integrals, which means I'm going to rewrite this. I'm going to factor the bottom. And then I'm going to see if there's a way I can rewrite this as a over n plus b over n plus 1. Remember, this is the way we do partial fractions. We had, on the denominator, we had 2 distinct linear factors, right? Distinct linear factors, n and n plus 1. And so I have some constant a over n plus some constant b over n. So yeah, now you clear the fractions out, and you get a times n plus 1 plus b times n. We've done this before, so I'm going a little bit fast here. To do this, I'm going to just do the shortcut method, which is just to plug in some values for n. If n is 0, then I get a is 1, right? If I replace all my n's with 0, I should just get a is 1. And if I let n be -1, I should get that b is -1. Do I need to show that work, or can I trust that you could do this? Yes? We're good? Thumbs up? Okay. So what we're saying is 1 over n times n plus 1 can really be written as 1 over n minus 1 over n plus 1. So what I did is I replaced the a with 1, and I replaced the b with -1, and I put that negative out here. So the reason I did that is because now what I'd like to do is I'd like to rewrite this series this way. Sum n equals 1 to infinity, but instead of that expression up there, I'm going to write 1 over n minus 1 over n plus 1. We have any questions on that? We have reached a critical point, a critical point. Do not write this down. Do not write this down. What did I do?
You split it into two harmonics.
I split it up, right? It seems reasonable to do that, right? That you should be able to split up if you have a sum and you have two things being subtracted, that you should be able to split it into two sums. This is not allowed, okay? This is not allowed in general unless both of these converge. So if you looked at 1 over n and you said, hey, yeah, maybe that 1 over n turned out to be geometric. And you're like, oh, yeah, that converges. Then you look at this over here and you're like, oh, yeah, that's also geometric. That converges. If you have two convergent pieces within a sum, then you can split it up. But if one or both of them are divergent, you are not allowed to split them up. It's against the rules, all right? Unfortunately for us, those individually, as I think Hunter pointed out, are constant over linear, constant over linear. These are both harmonic, right? And so individually, these diverge, right? Diverges, diverges. So you are not allowed to split it up. You cannot. Y'all still with me? All right. So that means we're stuck here, okay? Like, we got to figure out what to do with this. So when everything seems like it's kind of failing, one thing you can do is just start plugging in values, like just start plugging in the values of n. So let's try that. If I plug in 1, what would I get? I would get 1 over 1 minus 1 over 2, wouldn't I? Plus, now when I plug in 2 for n, I would get 1 over 2 minus 1 over 3, right? And then I plug in 3. So I get plus 1 over 3 minus 1 over 4. And I keep doing this, right? Plus, then you get 1 over 4 minus 1 over 5. Do y'all see it? That goes forever. Do y'all see what happens? Do you see this? 1 minus a half plus a half, minus a third plus a third, minus a fourth plus a fourth, minus a fifth plus a fifth, right?
It just goes to 1, doesn't it?
Well, those are going to start canceling each other out, right?
Yeah.
Okay, so how do we do this? We see a pattern. We see that because we completed the square, right? We complete, what the hell are you talking about, Robert? Because we did partial fraction decomposition, right? We now see a pattern of cancellation that would never have been apparent to us if we just did the original series. Like if you just did this and just started plugging in values, right? Plug in 1 here, what would you get? 1/2, right?
Yeah, it'd just be 1/2.
And then plus plug in 2 now. What would you get?
1/12?
Careful.
Something like that.
2 squared,
2,
right?
yeah, 6.
Or
1/6.
6, you get 1/6.
Then
And
1/12.
Now you plug in 3. 3 squared, 9 plus 3, 12. Yeah, I'm sorry, I thought I heard something else. Plus, see, that's what would happen, right? If you just started with the original, do you see there's no minuses in here anywhere? Nothing's canceling, right? You're just doing a half plus 6 plus 12, blah, 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 right? So the only way to see that there is actually something happening with canceling is to do your partial fraction decomposition. Tricky, huh? So what do we do? We're not done. We're not even close to being done. What we have to do is go back to what I started this with. If we're given a series, the whole idea is to see if we can come up with a formula for the nth partial sum and then take its limit as n goes to infinity. This step is our next step. Can we find a formula for S sub n? So let me write down, what is S sub n? S sub n is basically this sum out to n, right? Out to n. So I would start 1 over 1 minus a half plus, and then I go 1/2 minus a third, and then plus a third minus a fourth. But see, I'm going to stop, aren't I? I'm going to stop. I'm going to stop when I get to n. So what's the very last term look like? So what would be the very last term if I go and I stop at n?
1 over n minus 1 over n plus 1.
1 over n minus 1 over n plus 1. It's the original little sequence formula here, right?
Yeah.
Isn't it? Okay. Everyone understand that? That's me stopping at n. Now what I do is this. I'm going to write the one that would have been in front of that one. So this is what happens when I plug in n. This is what would happen when I plug in n minus 1. One less than n, right? So like if I stopped at 20, this would be 19. If I stopped at 100, this would be 99. So if I stop at n, this one here would be n minus 1. So what would you get if you plugged n minus 1 into this formula? 1 over n minus 1 minus 1 over n. So basically what I've done is I've taken 1 away from each of these n's. What would the one in front of that one be? Well, take 1 away from these n's again. 1 over n minus 2 minus 1 over n minus 1 plus, and then that would keep happening, right? That way, and these keep coming together like that. I have a bunch of crap in the middle. That is my formula for S sub n. Brandon, you all right? The question is, why did I do all this? Because now what I'm going to do is I'm going to start to recognize the pattern of cancellation. So I know that this negative 1/2 will cancel with that positive 1/2, right? This negative 1/3 will cancel with that positive 1/3. How about this negative 1/4? Is it going to go away?
Yeah, the next one will have a positive 1/4.
So the next one in here would go away, right? All right. What about this 1 up front? Does it cancel?
It shouldn't cancel, but it can be rectified to just a 1.
Okay, it is a 1, but there's nothing that cancels it, right?
Yeah.
It's this second. See, when we look in this parenthesis, pay attention to my language here. When I look in this parenthesis, the second guy will be killed off by the first guy 1 parenthesis down. The second guy in a parenthesis is killed off by the first guy in the parenthesis 1 down. The second guy is killed off by the first guy 1 parenthesis down. Okay, so what about this one right here? This guy right there. Can y'all see my cursor? That's a second guy in the parenthesis, right? Second guys get killed off by
The first guy. The next
first
one.
guy 1 down. So those two kill each other off. How about this second guy? This second guy gets killed off by the first guy 1 parenthesis down. How about this guy? This second guy.
It's the end. It wouldn't get killed off.
It's the end, right? There is no 1 parenthesis down anymore. This guy is still here, right? That guy's still there. This guy's still here. All right, I'm not done. I'm not done. There was one here I didn't look at. This one right here. How about that guy? Does that guy go away?
He
Well,
he should.
That's the first guy, right? First guys are killed off by
The second guy in the one
second
before.
guy, one parenthesis before. I'm actually going to type this out. I'm going to actually establish what the pattern is. Second guys, do you mind me calling second guys? You know what I'm talking about? Second guys cancel with first guys, one parenthesis down. Another way I could say that is first guys cancel with second guys, one parenthesis up, right? That's the pattern that I've established. So this one right here is a first guy. First guys are killed off by second guys, one parenthesis up. Well, is there a parenthesis up here? Absolutely, right? There is. I mean, it's a dot, dot, dot. It should be there. So this guy's going to get killed off by something in the dot, 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 just like this negative 1/4 was killed off by the next one inside that dot, dot, dot. And all the guys that are in here are all going to do the same thing and cancel each other out, right? So at the very end of all of this, the only thing left is what's in yellow. And so S sub n is 1 minus 1 over n plus 1. Notice that everything in the middle, right? All this crap in the middle right here, just kind of what? Kind of just, right? Just collapsed out like a bridge. Think of it like a bridge. If you had a bridge going across a span, right? And then the bridge collapses, right? Everything falls and all you're left with are the two pillars on the end. That's why we call this a collapsing series, because everything in the middle kind of collapses out and you just get the two ends. It's also called a telescopic series because old school telescopes, the ones that you put your eye in, right? And you'd look and then they would fold them up, they'd collapse them down like that. And so the ends would come together. That's basically what's happening, is the two ends of this are coming together. Okay, we're not done. We're not done. We now need to take the limit as n goes to infinity of this. So the limit as n goes to infinity of that formula, 1 minus 1 over n plus 1, is equal to 1. And that's what the sum converges to. So if you go back up to this and you look at what we had, 1/2 plus 1/6 plus 1/12, if we were to continue to do this forever, this would converge to 1. How do we know? Well, because we did partial fraction decomposition, we rewrote it in a different way. We noticed it was a collapsing sum. We found a formula for S sub n. We took the limit of that S sub n and we got 1. That's how we know.
Is this how you need to solve it anytime there's a telescoping series? Telescopic?
You have to come up with a formula for S sub n. You have to, all right? In fact, if you just see, because if you take the test, let's say you were taking the final exam and you get to this point right here, all right? And you go, oh, yeah. Oh, all that's left is 1. You give me your answers 1. I will not give you full credit. Because there are times where the thing at the end doesn't go to 0. And then you don't get collapsing, you actually get divergence. So you have to be careful. You can still have canceling and have divergence. So you've got to check what S sub n is, you got to find it. This was an easy example. Let's do a harder one, okay? Let's do this one. All right. I don't know why it's leaving those dotted things. It's weird. There was an update on the little program I used to do that, and now it's leaving these dots. Okay. Let's just kind of run through the things here. Nth term test. Okay. Look at the sequence. Look at the sequence. let n go to infinity. Goes to 0, I know nothing, right? Okay, so I know its n-term test fails. It's not geometric because there's no n in an exponent, okay? Not geometric. It is not harmonic because it's not constant over linear, it's constant over quadratic. If I start plugging in values for n, like let's just start plugging in values. If I plug in 1, if I plug in 1 here, I get -4 over 3, right? Plus, now if I plug in 2, I get -4 over 6, I think. And then plus -4 over, I plug in 3, 9, and it's 15, I believe. Is that right? Something like that. This is not, there's no pattern of anything canceling. It's just a negative number plus another negative number plus another negative number, and this goes forever. So I'm starting to think, you know what? Partial fractions. Let's try it. So I'm going to do -4 over, let me factor the bottom, n plus 2, and that's going to be equal to a over n plus b over n plus 2. Clear the fractions. Let's let n be 0. If I let n be 0, I think I get a is -2. And if I let n be -2, I get +2, I believe. Somebody check that. I'll just do it. Okay, if n is 0, kills this off, and that gives me 2a equals -4, it's -2. And if n is -2, it kills this one off. And if that's a -2, b equals -4, that means b has to be +2. So I'm doing that very quickly. I'm expecting you could get that done. Now I'm going to rewrite what this is. Sum n equals 1 to infinity of, okay, a over n, so -2 over n, plus b, which was 2, over n plus 2. I'm tempted to want to split this into 2, but I can't because these are both harmonic. And so they diverge, and so I can't split it. So my best bet is to probably just start writing things out, right? Any questions, what I've done so far? Okay, let's plug in 1. -2 over 1 plus 2 over 3. Yes? Okay, next one, plus. Now plug in 2. -2 over 2. Notice I'm not simplifying that, like I'm not making that -1. I'm not going to simplify anything. Plus 2 over, I'm plugging in 2 now, right? So that should be 4. Plus -2 over 3 plus 2 over 5, I believe, right? Now I'm plugging in 4, so -2 over 4 plus 2 over 6 plus ... Are we getting the same canceling we were getting before? Not exactly, right? Not exactly. But notice this, that +2 2/3 will be killed off by that -2 2/3. And this 2/4 will be killed off by that -2/4. I have a different sort of pattern of cancellation here, don't I? It's not what we had written down here before. It's not second guys cancel with first guys 1 down, or first guys cancel. It's not that, slightly different. How could I say this? Second guys, what, cancel with first guys, what?
2 parentheses down.
2 parentheses down, 2 parentheses down. Does everyone see that pattern? That the second guy in a parenthesis will cancel with the first guy in the parenthesis, but 2 parentheses down. Second guy cancels with the first guy, 2 down. Let's write that backwards. You could say first guys cancel with second guys, 2 parentheses up, right? That would be like the reverse direction. This one is a first guy. He cancels with the second guy, 2 up. Does this make sense what I've typed up here? Does that I mean, the way you do these problems is that you have to establish the pattern. You don't have to actually write that down. I'm just writing it because I'm trying to help you understand this. That's the way I see it though. So what comes next?
Now we find our nth term.
We need a formula for S sub n. All right. So here, unfortunately, I'm going to have to write this again. -2/1 plus 2/3 plus -2/2 plus 2/4 plus -2/3 plus 2/5 plus -2/4 plus 2/6 plus, then I'm going to have ... right? All the other stuff. Let's go to the other end and put the very last one in. The very last one is basically just this formula right here that we have. -2/n plus 2/n plus 2. The one in front of that is this same formula, but subtract 1 from both of the ends here on the bottom. So -2/n minus 1 plus 2/n plus 1, because you're basically taking 1 away from that denominator. I have to show you another one, because in order for you to see the pattern, the cancellation, you need at least 2, you need a parenthesis 2 down to see the canceling. So -2/n minus 2 plus 2 / just n. You could throw another one in there if you want to. You don't have to. I'm out of room, so I'm not going to. Let's figure out what goes away. I'll start with this one. That's a first guy, right? That's a first guy. And in order for a first guy to cancel, I need a second guy 2 upstream. I don't have anything upstream, do I? To the left. So that guy's staying, not going anywhere. Now I'm going to move to the next one. That's a second guy. He will cancel with a first guy 2 down. So this and this are gone, right? Move to this one. That's a first guy. For him to cancel, I need a second guy 2 upstream. I don't have that, do I? I do not have any, I do not have a parenthesis, 2 parentheses up. So that's staying as well, isn't it? What about this second guy?
Cancels.
Gone, right? With that one. All right, what about, now we're here, this second guy. Is that second guy gone?
Yeah, that should cancel.
Yeah, we need a first guy 2 down. Where is he? Somewhere in the ... right? Somewhere in the ... is where that one goes. This one is a second guy. I need a first guy 2 down to the right. I've got him. He's in there somewhere, ... right? So all of this has gone away except for what's in yellow. And then I think what I'll do is I'll go to the other end and I'll work my way this way. So this is a second guy, and a second guy is going to need a first guy 2 down to the right. I don't have anything to the right, do I? Still here. This one is a first guy. It needs something 2 up. I have him. There he is right there. Gone. Second guy, I need 1 2 parentheses down to the right. I don't have it. stays. First guy cancels with, no, not that one. Cancels with something in here. This guy cancels with something in here. So S sub n is everything in yellow. I'll clean those fractions up. That's -2 plus -1 plus 2 over n plus 1 plus 2 over n plus 2. That's just all the stuff in yellow. I have a nice formula for S sub n because everything is collapsed, telescopic, whatever you want to say. Now we're ready to figure out what S is. The sum that we're looking for is the limit as n goes to infinity of this thing. Negative, I'll just say -3 is all right. -3 plus 2 over n plus 1 plus 2 over n plus 2. And that converges to 3. -3, sorry, because both of these guys go to 0. The sum converges to -3. It's kind of interesting, huh? There's really like no limit on how far down these cancelings can happen. So like if I had given you a problem where you see how we factored and it was n plus 2 and the canceling happened 2 down. If this was n plus 4, the canceling would happen 4 down. So it doesn't have to be, the canceling doesn't have to be in 2 parentheses right next to one another or even 2 away. Sometimes it's 3 away, 4 away. Now I'm not going to give you anything crazy like, you know, like 8 away, but you just need to be prepared that it's not necessarily going to be like our first example where it's right next to it. All right, we have one more example. Natural log. All right, real quick, nth term test. Nth term, we got to run the nth term. Take a look at this. Let n go to infinity. You get infinity over infinity. So I can do L'Hopital on the inside. What would I get if I did L'Hopital in here?
1 over 1.
1 over 1, okay, which is 1. And what's the natural log of 1?
Natural log.
0. And so the nth term test tells me nothing. Right? What I'm saying is if I take the limit as n goes to infinity of the natural log of n plus 3 over n, I get 0, so this fails. This is the nth term test that I'm running there. Natural log of 1 is 0. All right, well, it's not, what's that thing called? Geometric? It's not geometric, right? It's not harmonic for sure. So really, I think all we have is telescopic at this point, but partial fraction decomposition isn't really going to work here because we don't have like what we've had before, right? And if we just start plugging in values, right, what would happen? If we plug in 1, we get natural log of 4 over 1 plus natural log of, then it would be like 5 over 2, and then plus natural log of 6 over 3 plus, and see, there's no minuses anywhere in here. So I'm never going to get any canceling or telescopic stuff to happen. Unless, yeah, go ahead. What?
No, sorry about that.
No, it's okay. Unless I realize this, that I can rewrite this as natural log of n plus 3 minus natural log of n. That's just a property of logs, right? We have a property of logs that says if you have a logarithm and you have division inside, you can split it into two logs with subtraction. How do I know that? Because this morning, I actually covered that in my college algebra class right here. We called it property 10. If you have division inside of a single log, it splits into two logs with subtraction. It's hard to explain to a college algebra student that this stuff's going to come up later.
I was doing that literally yesterday, and it was like,
Yeah, good.
it's like, this is how it works, man.
So this is actually a good thing, because if I do that and then start writing it out instead like this, if I plug in 1, I get natural log of 4 minus natural log of 1, right? That's what I get when I plug in 1 into this. Plus, now we do natural log of 5 minus natural log of 2. So far, no canceling. Let's keep going. The next one will be natural log of 6 minus natural log of 3. Anything cancel yet? Nope. Plus natural log of 7 minus natural log of 4. Ah, there's one, right? Look, this one here and that one there would cancel. Wouldn't it? And then if I do another one, I'm going to run out of room here, but let me just squeeze one more in here. I'll have natural log of 8 minus natural log of 5. And there, I'm going to get another canceling, this one with this one. So what's the pattern here I'm seeing? First guys cancel with second guys.
3 parentheses down.
Is it 3? 1, 2, 3 down. 3 parentheses down. Or the other way to write that would be second guys cancel with first guys 3 parentheses up. We have to finish this off. Okay, let's finish it off. Formula for S sub n. Right? I have a lot to write here, don't I? I have a lot to write. I'm going to save myself the time and I'm going to copy and paste. Copy that. So here's S sub n written down. I'm going to make it smaller because I need space. In fact, I think I'm going to move this whole thing to the left. This. Okay, that's S sub n so far. You okay with that? I just wrote out the first group. Now I'm going to say plus dot, dot, dot. And then what's the very last one going to be? We'll have
Our starting formula that
natural log
n
of n
plus
plus
3
minus natural log n. I'm sorry I'm having to write this so small. Natural log of n plus 2, I subtract 1 from each one, minus natural log of n minus 1. So I'm just subtracting 1 from each of those. I've got to go down further for me to see this. I'm going to run out of room. Natural log of n plus 1 minus natural log of n minus 2. See, I still don't have the canceling in there. So I'm going to move it to the line below and then put the next one in front of that. Natural log of n, there it is, minus natural log of n minus 3. Plus dot, dot, dot. Now let me do just the stuff that cancels. What was it? The first guy cancels with second 3 down. This guy will cancel with that one there. How about this natural log of 6? Is it gone? This first guy here? Is it going to go?
Yeah, there will be something in the ... that'll kill it.
Yeah, something in the ... is going to kill that. So we've got this is gone. This is gone. That one, first one's gone. Natural log of 7 should cancel with something in the ... because it's a first guy. It needs something 3 down from it. This natural log of 8 should cancel with something in here. Now, the things that are still here, I've got this right here. That's a second guy. You need to have something 3 up from it to cancel, which I don't have anything up from that. This one's still here because it has to have something 3 up. There's nothing 3 up. And this one's here, right? Those are all there. On the other end, this negative natural log of n cancels with that. This one should cancel with something in the ... So all these second guys are gone. But the first guy here, here, and here all stay, don't they? Because they, in order for these first guys to cancel, I would need second guys 3 down to the right. I don't have anything. So here's what S sub n looks like, everything in yellow. Negative natural log of 1, minus natural log of 2, minus natural log of 3. Then I still have plus natural log of n plus 1, plus natural log of n plus 2, plus natural log of n plus 3. Now take your limit. As n goes to infinity of this.
Natural log goes to infinity at infinity, right?
Goes to infinity, that's right.
So this just diverges then.
This goes to infinity, that goes to infinity, that goes to infinity. We're adding all those up, that's still infinite. This right here is a number. This right here is a number. This right here is a number. So you got 3 numbers added together and then you're going to add infinity. This thing blows up. It goes to infinity, which means that this series diverges, which is why you have to figure out the formula for S sub n, because it's not always going to collapse away and just leave you with some stuff in the front. It's not always going to be that case. So this diverges. These are fun. I like these. Any questions? I didn't mention this, but it's probably obvious when you looked at the take-home exam that the material and take-home exam actually stopped where class ended last class. So today's material is not on that take-home exam. So don't be trying to do like harmonic stuff, or none of that should be on that test.
Just the nth term test and geometrics.
Yep. All right, we have 20 minutes. I'm going to say that we are officially done with 8.2. Recap, geometric, harmonic, right? Telescopic. The only series we can find sums of are geometric and telescopic if they converge. If they converge. Let me just double check my notes, make sure. Okay, the very last note on this was that alternate notation for geometric series. So this is just me showing you, you can start it for geometric series, that you can start at n equals 1 or you can start at n equals 0. The formula changes ever so slightly. These 2 versions should be known, become familiar to you. All right. Ready for 8.3? Ready or not? Let's take a 30-second break. I'm just going to refill my drink. I'll take a deep breath. Yes, Ricardo, we can talk after class is fine. All right, so 8.3. So what we're going to do now is we're going to kind of shift gears and realize, you know what, there are a lot of series out there that are not geometric, not harmonic, and not telescopic. But we still want to know whether or not they converge or diverge. We're going to kind of give up on trying to find what the sum is on series because it's very hard to do. Very difficult to do. And you might be going, well, just knowing it converges doesn't seem very valuable. Like, okay, great, it converges, big deal, but you don't know what it converges to. How's that helpful? It is. It's all we need for what's coming later, which is the Maclaurin and Taylor series. We just need to know when they converge so that we have a valid domain, so to speak. So just hang tight on that. Just take faith in the idea that convergence and divergence is all we need for where we're headed. All right, so what's the main idea? That's pretty much probably what I'm saying right now. Well, where'd that little thing go? Let me make this bigger. All right, yeah, so this is me just basically saying that, all right? All right, preliminary idea. When we're trying to determine the convergence or divergence of a series, all right? When we're trying to figure out whether or not a series converges or diverges, there's a few little subtle things we need to realize. Let's say that we have a series and we know it converges, all right? Notice where the index starts here. See, it starts at 1. What if I tell you that that series converges? Well, then if I start the index at 5, that should still converge. Because what we're saying is if you add up an infinite number of terms, right, starting with 1, and that adds up to be a number, then if you start later in the series and add up fewer terms, that should still converge as well. So we can start at 1 or 5. It does not impact the convergence. The conclusion of convergence doesn't impact. Now, does it impact the actual sum? Yes. If you change where you start, it will change what it converges to. It just doesn't change the fact that it converges. So a finite number of terms has 0 impact on convergence if you change it by a finite number of terms. If you take a finite number of terms out, or if you put a finite number of terms in, it's still convergent. The same thing applies for divergence. If you have a series that diverges, then if you change it to a different starting place, what you're doing is you're taking out a finite number of terms. Well, if it's infinite to begin with, taking out a finite number of terms has no impact on the fact that it's infinite. It's like me asking you to subtract 10 from infinity. You're still going to have infinity, right? Or even if I add 10 to infinity, it's still infinite. So just keep that in mind, okay? We need that as we move ahead. Removing or adding a finite number of terms to a series has no impact on its convergence or divergence. All right, so this section is called the integral and comparison tests. So what we're going to do now is we're going to develop 2 new tests for figuring out whether or not a series converges or diverges. One of them is called the integral test. The other one is called the comparison test. We're going to start with the integral test. So I'm going to try and explain this to you visually first. Let's go back to earlier this semester when we were doing improper integrals, and I asked you to find the area under a curve from 1 to infinity. Okay, so we're back to area under curve, not series, just area under curve. We had some conditions. We said that, you know, we had to have a continuous function on the interval. We had to make sure that the function was positive, always above the x-axis, and that the function was decreasing. As long as we had those things, then we would have a graph that looked something like this. And so as we move out to the right forever, we could talk about, you know, from 1 to infinity, we could talk about the area underneath that, right? Sometimes the area was finite, sometimes it was infinite. It depended on the function. And here I'm giving you the example 1 over x squared. This is what 1 over x squared looks like. This actually converges. If you remember, if the power here is bigger than 1, we get convergence. If the power is less than 1 or equal to 1, we get divergence. So if I change that power, I'll get convergence. If I go this way, that's going to be a divergent integral. This is just to remind you of what we talked about before. So now, what's the integral test? Let's take this function f of x equals 1 over x squared. That is not a sequence. That is a function, right? That is a function. The area under that, this area converges. We showed that already in this class. Go back in your notes. We showed that the integral from 1 to infinity of 1 over x squared dx, we actually showed that this was equal to a number and that it converged, all right? So this purplish area under that curve is finite. Got it? It's got a finite area under there. Now what I'd like for you to do is I'd like for you to say again.
You know what, that makes sense. Never mind.
Okay. What I'd like for you to consider now is the sequence 1 over n squared. Okay, the sequence, not the function. That would look like this. It would be all these dots, right? All these dots along this curve. The question is, if you add up all these things, right? So, you know, what does this sequence look like? That's right. If you were to add up all of these things, the question is, does this converge or does it diverge? So check this out. This is pretty badass, what I'm going to do, all right, to convince you of this. What I'm going to do is this. Let me back it up. Starting with this very first point right here in my sequence, I'm going to construct a rectangle. That rectangle is going to be the same height as the sequence point, and the width of it is going to be 1. Do you all agree that that area right there is finite, right? That's a finite area right there? Okay. Now, let's move to the right to the next sequence point. Do the same thing. Go up to that sequence point, draw a rectangle, boom, got it, right? That area is finite as well. And I'm going to keep doing that for each of the sequence points in here forever. Isn't the area of the blue, let me just look at these, no, not blue. Isn't the area of the stuff in pink, the pink rectangles, aren't all of those areas added together smaller than the integrals area? Right, because the integral includes not only the rectangles, but this other extra stuff. So if this integral is finite, right? If the integral is finite, then the sum of those rectangles are finite, aren't they? Now we do have one additional one, right? This one right here, this guy right here, that is an additional rectangle, but it's only one number, right? So, you know, if I'm telling you that all this stuff here, all these purple boxes or rectangles, if that's finite, because it's got to be smaller than this one, smaller than the total area under the function, then adding one rectangle should still be finite. Agreed? So the idea is that if we're looking at a sequence, right? The way we're going to think about this is, let's say we started with this and we said, hey, does this converge or diverge? What we're going to do is we're actually going to convert it to a function first. Then we're going to do this integral on it. And if that number is finite, well, then so is the sequence. So whatever the integral does, the sequence does. And that's the visual kind of reason why. Does it make sense to you? Any questions on the geometry of that? All right. Now, what if our sequence, instead of, hold on, what is this one? Why do I have two of these here? Let me show you an example where you have the opposite happening. So right now we're looking at 1 over x, not 1 over x squared. So the equivalent sequence to this would be 1 over n. Wait a minute, don't we know what 1 over n does as a sequence? It's
Yeah,
harmonic.
that's harmonic. It diverges.
Diverges, right? Okay, the reason it diverges is because if we convert that to a function of x and do this integral 1 over x dx, this goes to infinity. We, again, go back and check in your notes, this diverged, all right? So how am I going to convince you that to do this, like imagine that wasn't harmonic, just imagine that it was a series, we don't know what it does. How can I convince you geometrically that we can just look at the integral? So I'm going to do the same sort of thing. I've got a sequence in here, right? There's the sequence of points. And I'm going to draw rectangles again, but watch how I draw them. I'm draw them a little bit different. I'm going to go and draw them from the point up to the right and then down. Do you agree that the area of that box is bigger than the area underneath the curve right there? And I can do that for each of those like this. The area of each box is more than the total area underneath the curve, right? So if I know that the area under the curve, right, this area, if I know that that area is infinite and my boxes add up to be more than that, right, then that means that this series, right, would have to be bigger, sorry, wrong way, would have to be bigger than infinity, which means that it would diverge. So what does this all mean in the end? What does it mean to you? What are you going to do with this? Right? This was just me trying to explain it visually, like what's going on. How are you going to utilize all this? The conclusion. Given a function f, which is continuous and positive and decreasing, which is continuous, positive, and decreasing, consider the sequence, which is basically the function restricted to the natural numbers. If the integral of the function converges, so does the sequence. If the integral of the function diverges, so does the not the sequence, the series, right? So does the series with that sequence. That's the conclusion, and that's in your test. Remember that. Go look at your test, the sheet with your test. The integral test is on there, and it says basically whatever the integral does, that's what the series does. I don't have a lot of time, but I can at least set one up. Let's do this one. Let's get it started. So take a look at this series. Sum n equals 1 to infinity of n over e to the n. It's not geometric. Why? Well, you do have n in the power, don't you? But you also have n in the base, like just n by itself on the bottom. So this can't, geometric, the n has to be up in the exponent and only in the exponent. So it's not geometric. It's not harmonic because, well, it's not constant over linear, right? It's not telescopic because there's nothing you can do here to pull this apart and try and get things to fall out. It's not going to happen. You can try the nth term test if you'd like. Nth term. Take the limit as n goes to infinity of n over e to the n. If you do L'Hopital one time, you'll get 1 over e to the n, and that goes to 0, which tells you nothing. It fails. So the only thing you have left is the integral test. At this point, that's all we have left. So what I'm going to do is I'm going to look at the sequence and I'm going to create a function of x out of it, which would be the function x over e to the x. And what I'm going to wind up trying to do here is the integral from 1 to infinity of x over e to the x dx. I'm going to do this improper integral. If that turns out to give me a number, a finite number, then that's going to tell me that this sequence converged. If this integral turns out to diverge or become infinite, then that's going to tell me the sequence diverged.
Why couldn't we
whatever
just
the
do this
integral
for a
does-
harmonic series, Professor?
Say again?
Why couldn't we just do this for a harmonic series, Professor?
That's exactly how you can prove a harmonic series diverges. You can prove a harmonic series diverges using this method. I proved it doing the 1/2 thing just because we didn't have integral test yet, right? In fact, if you look at my notes, right here, we're going to get to it, P series. I will show this graphically, but we could prove it using the integral test, but we're not going to. So we're just not going to go through that work. So look, we're not done. There's more I need to talk about with this. Before you can do this, okay, before you can even go here with this, you have to have some conditions. Your function f must meet some conditions for you to be able to do this test. And the conditions are right here, how to use the test. So if you're given a series, like I just gave you one, right? N over e to the n. I give you a series. First, you're going to convert the sequence to a function of f. Okay, got it. F of x equals x over e to the x. Did it. The next thing we have to do is we have to make sure that that function is continuous on the interval 1 to infinity. Make sure it doesn't have any discontinuities, no weird shit happening to the function. We also have to show that the function is always positive, that the function always stays above the x-axis. We also have to show that the function is decreasing. How do you show that a function is decreasing? Cal 1, to show a function is decreasing, you look at the derivative and show that the derivative is negative. So we're going to have to take the derivative of that function and show it's negative. And then after you've done all that, then you can do the integral. After you do the integral, you'll have your conclusion. The biggest mistake I see with integral tests is that students will set up the integral, they'll draw the correct conclusion, everything's beautiful, but they never verify these things right there. They never show any of that. And that's incorrect because you must make sure that the function you're looking at is continuous, positive, and decreasing. So that's where we'll have to end today. As far as homework, everything in 8.2 is pretty much on the table, and you have a take-home exam. So, yeah,
To be honest, that prioritizes in my mind.
Yeah, I'll be around. Okay, if you want, I put on the test that you could work together in groups no more than 3, but you have to write on your test, you know, who was in your group, and I've said not to reach out to help, you know, tutors or friends that are engineers. You know, just keep it between your classmates and myself, but I am available to you. You just need to reach out to me. So if you're working on something, you have a question, and I really mean this, okay? Because when I grade this, if you do something that you assumed you could do, then without like checking with me first, and it's not okay, then that's going to cost you, because I'm giving you the opportunity to ask me like, hey, we just want to make sure that this is okay. Like, I use the computer to do this. Is that okay? Because certain things are and certain things aren't. So don't hesitate to reach out to me. Send me a text, send me a picture of what you're working on, call me. If I'm available, I'll come on Zoom and meet with you. You know, I really would like there to be some interaction, some dialogue going on between myself, you, or you and your classmates. You know, because learning math, at least as you progress through your STEM, you know, I think there's a huge benefit into collaborative learning. And, you know, showing up and talking to each other about something and having someone explain it a different way, and or maybe you helping someone understand something, just makes everything go in a little bit better. So, okay, that's it. Y'all have a good day. I'll hang out here, Ricardo, if you want to talk. Have a good day. Have a good weekend. Have a good Easter. If I don't
Take
talk.
care. Have a good weekend.